right? Up until now, we've mostly been using Cartesian coordinates or rectangular coordinates to locate points in two-dimensional space. So, right, typically what we've been doing in two-dimensional space, right, is in our XY coordinate system, we've just been going over X and up Y to get to the point X comma Y. But we could also view this as going, instead of over X and up Y, we could also view it as going, say, an angle theta. So like, going up like that. So picking the angle theta and then going a distance of R. So this coordinate could also be R comma theta in polar coordinates. And so we can see from this triangle, from this right triangle, ways to relate the Cartesian coordinates to the polar coordinates. I would probably start off with the Pythagorean theorem. I can see that x squared plus y squared equals r squared, which is what we use, right? But if you wanted to solve for r, you could say that r is the square root of x squared plus y squared. And we also have that, let's see, we can use our trig to say that sine of theta is y divided by r. That's going to give us that y is equal to r sine theta. Similarly, cosine theta is equal to the adjacent over hypotenuse, x over r. So we have x equal to r cosine theta. And lastly, tangent theta is equal to y over x. So if we wanted to find theta, we could find the inverse tangent of y over x. This one you have to be a little bit careful with because the inverse tangent only gives you values of theta between negative pi over 2 and pi over 2. But if you have an angle that's like over here, that's something different. Or maybe over here, right, that's something different. So you have to be a little bit extra careful with the theta one, but it's not too hard if we know what the picture looks like. So let's look at some examples. With polar coordinates, for examples, the polar coordinates, a negative value for r means you face the direction of your angle theta and you move backwards instead of moving towards it, right? So let's look at some examples. Let's find 3 different polar coordinates for the Cartesian coordinate xy equal to 0, 3. Okay, I find it helpful to draw a picture. So let's see. So let's leave it up here. 1, 2, 3. So I could either do an angle of, say, pi over 2. So I could do one answer as r theta is a radius of 3 and an angle of pi over 2. Sorry. Another potential answer would be to go this way. I could go negative 3 pi over 2. So I could also try r theta is negative 3 pi over 2. Sorry, let's just write the r first, apologies. 3 comma negative 3 pi over 2. That would also be totally valid. Or we could even say, I'm going to go all the way this way with an angle of positive 3 pi over 2. And then have a negative radius, so a radius of negative 3. All of these polar coordinates represent the same point. Let's look at another example. Let's say I wanted to do the point about 2, 2. Okay, so let's actually draw it. So here's the point 2, 2. And can anybody tell me what angle with the x-axis does that make? I know you guys know. Nobody wants to tell me?
A 45-degree angle?
Exactly. So we know that this angle is pi over 4 radians, or 45 degrees. So one answer for that point would be an angle of pi over 4. And the radius of not 2, right? The radius isn't 2. The radius is, well, let's see, we know that x squared plus y squared equals the radius squared. So that's going to be 4 plus 4 equals the radius squared. So let's get the radius is going to be the square root of 8. That'd be one option. Or we could go to the opposite angle there, which would be pi over 4 plus 1/2 of a revolution. So pi over 4 plus pi, which would be 5 pi over 4. And use the negative. Right, so then we're going in this direction, but we're going negative, so we're going back that way. And what else could we do? I don't know. We could try. I guess we could try using a different angle, right? Instead of using pi over 4, you could either go backward 7 pi over 4, that would work, or you could even go pi over 4 and the whole revolution, right? So you go like pi over 4 plus 2 pi, which would be 9 pi over 4. That would definitely work. My 9 pi over 4 is a full revolution and then another pi over 4 worth. More examples I want to do? No, not really. Something else. So there's a lot of things. Ooh, looks like it. There's a number of things we do with Cartesian and polar coordinates. One thing is to convert between equations. So like, and usually, most of the time, I'd say we're usually converting from polar equations to Cartesian equations, but we can also go the other way. So for example, I want to convert x equals 3 to polar. Typically, not always, but typically when you're writing a polar equation, you usually write r as a function of theta. So it's like we usually write y as a function of x, we usually write r as a function of theta. So I'm going to replace x with what it's equal to. X is equal to r cosine theta. So I'm going to have r cosine theta equal to 3. And then solving for r is equal to 3 divided by cosine theta. Or if you prefer, r is equal to 3 secant theta. That's kind of interesting. This line, x equal to 3, is also the equation r equal to 3 secant theta, which makes sense if you think about it. So let me actually point out how this works. Right? If your angle is 0, sorry. If your angle is 0, secant of 0 is 1, so you get 3 times 1, which is 3. So your radius is 3 and your angle is 1. So your angle is 0, your radius is 3, right there. And then if your angle is, say, like pi over 6, secant of pi over 6 is annoying. Cosine of pi over 6 is the square root of 3 over 2. So secant of pi over 6 is 2 over root 3. So this is equal to 3 times 2 divided by the square root of 3, which is 2 square root of 3, which is about 3.4. So if you're going at this angle of pi over 6, you want to go 3.4, which that length there is the right length. And the right angle is, say, like pi over 3. 3 times secant of pi over 3, well, cosine of pi over 3 is 1/2, secant of pi over 3 is 2. So if your angle is 60 degrees, you're going to hit up here, where this length is 6. But all these angles, as they get bigger and bigger and bigger and bigger and bigger, secant of theta also gets bigger and bigger and bigger and bigger and bigger. So as the steeper your angle gets, the further you go to get to the point on the line x equals 3. It's kind of neat. In a similar way, if you want to find a horizontal line, you would end up getting r equal to something times cosecant theta. And a couple other graphs of things like y equal to x. So you could probably figure this one out by graphing it. Maybe not, I don't know. Here's y equal to x. So for this one, I'm noticing that every point, well, you're getting points of various radii, but all the angles are the same. So if we actually just replace y with r sine theta and x with r cosine theta, it's very tempting to cancel the r's, but we probably shouldn't. Instead, I would bring everything to one side and say r times sine theta minus cosine theta equals 0. So either r equals 0, which is always the origin when r equals 0, or sine theta minus cosine theta equals 0, which means sine theta equals cosine theta. And the only angle where sine theta and cosine theta are the same is pi over 4. So what this is saying is every point on this line has an angle of pi over 4 as a polar coordinate of a radius can be being anything and an angle being pi over 4. So any point here is, you know, some radius comma pi over 4, where the radii take on all values. Then you can get some funky stuff. You have something like y equal to 2x plus 1. So straight lines that go through the origin are always going to be just an angle, theta equals something. Notice, by the way, that this answer here, right? So this line is the line theta equals pi over 4. That one doesn't have r as a function of theta because there really isn't any r to have. If something like this, things are a little bit weirder. So then I'm going to replace y with r sine theta, x with 2 cosine theta, plus 1, x with the 2r cosine theta. Sorry about that. It's hard to see that now. I think it's x hard. So let me see if I can change the lighting a little bit here. So r sine theta equals 2 times r cosine theta. And here we're typically trying to solve for r. So bring everything to the left, or bring all the r's to the left. So r sine theta minus 2 r cosine theta equals 1. Factor out an r. So r times sine theta minus 2 cosine theta equals 1, and then divide by this. So r divided is equal to 1 divided by sine theta minus 2 cosine theta, which feels pretty funky, but is correct. Yeah. Let's look at a couple more examples. So let's look at, say, here's an easy one. X squared plus y squared equal to 16. You could replace x and y both with the respective r cosine theta and r sine theta. So you could say this is r cosine theta squared plus r sine theta squared equal to 16. And then getting this, you get r squared cosine squared theta plus r squared sine squared theta equals 16. Factor out the r squared, and you're left with cosine squared plus sine squared, which is equal to 1. So then this is just r squared times 1 equals 16. So that means r has got to be 4. Which again isn't surprising, right? Because we know that x squared plus y squared is equal to r squared, so we should have gotten this. So this is the equation where, right? This is the equation of a circle where the angle where the points are all the points on the circle. The radius is 4, and the angle can be anything. Totally works. Let's look at a different example. Also a circle. Let's move the center. Let's say we have the circle, I don't know, x squared plus, what am I going to say here? Yeah, y minus 2 squared equals 4. Yeah, that's just fine. So it's a circle, radius 2, center is the point 0, 2. Looks like this. Notably, one of its ends or one of its points touches the origin, or is on the origin. So let's go ahead and change this over. So x is going to be r cosine theta, quantity squared. Y is going to be r sine theta minus 2 quantity squared equals 4. Let's multiply it out. Get r squared cosine squared theta plus multiply this out, you get r squared sine squared theta minus 2 times another 2 is minus 4r sine theta plus 4 equals 4. Okay, we can cancel a 4 here and a 4 here. And r squared cosine squared plus r squared sine squared, that's just equal to 1. Sorry, to 1 times r squared. So we get r squared minus 4r sine theta equals 0. Then we can factor out an r. So we get r times r minus 4 sine theta 0. So we either get r equal to 0, which clearly isn't the graph. I mean, you do have that 1 point, or you get r equal to 4 sine theta. Which is interesting. Let's see one thing here. Yeah. So this is very typical. If you have r equal to something times sine theta, you're going to get a circle on the y-axis where the diameter of that circle is this number here. And so half of that number is what the radius of that circle is. And the center is typically at 0, whatever half of that is. And the same is true if r equals 4, if something cosine theta. So r equals 4 sine theta, you've got a circle with center 0, 2 on the y-axis. If r equals, say, like 6 cosine theta, you're going to get a circle on the x-axis whose center is 3, 0. And something to remember about these circles is you actually only need for theta to go from 0 to pi to get the entire circle, which is kind of weird. But it is true. Right? If you have r equals 6 cosine theta, when theta starts at 0, cosine is 1. So 6 times 1 gets you this point here. So here's the point, r is 6 and theta is 0. And then here's the point where the radius is pi over 4. And 6 times cosine of pi over 4 is 6 times root 2 over 2, which is 3 root 2. And then over here, you get when theta is equal to pi over 2, because cosine of pi over 2 is 0. So halfway around the circle, you've only gone from theta equals 0 to theta equals pi over 2. And then the other half of the circle, you're going to go from theta being pi over 2 to pi. And the reason it ends up down here is because when you go from pi over 2 to pi, you're in quadrant 2, and cosine's negative. So all these things that would be up here, reflect them back down there. Converting to Cartesian is a little weirder. It can be weird, it depends. Converting to Cartesian. So, for example, we have r equals 4 cosecant theta. I'm going to first write things in terms of sines and cosines. So I'm going to say r equals 4 divided by sine theta, and then multiply by sine theta. Because when I'm trying to convert to Cartesian, I'm trying to get things that look like either r sine theta or r cosine theta, or x or r squared, because they can change those easily. So r sine theta is going to be y. So r equals 4 cosecant theta is the line y equals 4. Or we could have something like this. R squared equals sine theta times secant cubed theta. So I would write this as r squared equals sine theta divided by cosine cubed theta. And it's very tempting at this moment to replace r squared with x squared plus y squared, but I would wait. So I don't know, I want this, I guess. R squared cosine cubed theta equals sine theta. Really, with every sine or cosine, you want an r multiplying it. So I'm going to multiply both sides of this by r. So r cubed cosine cubed theta equal to r sine theta. And then r sine theta is y. I can write this as r cosine theta quantity cubed, which is going to be x cubed. So I get y equal to x cubed. We know what that looks like. So yeah, this is kind of a funky, right? It's kind of weird that this polar graph would give you the cubic Cartesian graph. But interesting nonetheless. Well, let's get to the heart of things. So let's do some polar graphs. So here's a cardioid. R equal to 1 minus sine theta. And typically when graphing these, I kind of just make a list of points because there's not really, until you get a lot of practice in, it's really kind of hard to have a good kind of instinct about what these polar graphs look like. So, some angles, some values for R, some big angles like, 0, pi over 6, pi over 2, 5 pi over 6. I'm sure, pi. Let's see where that gets us. So plugging in 0, sine of 0 is 0, so 1 minus 0 is 1. Plugging in pi over 6, sine pi over 6 is 1/2, so 1 minus 1/2 is 1/2. Pi over 2, sine pi over 2 is 1, so 1 minus 1 is 0. Sine 5 pi over 6 is also 1/2, so 1 minus 1/2 is 1/2. And sine of pi is 0, so 1 minus 0 is 1. And if we go to 7 pi over 6, the reason I'm thinking pi over 6 is because sine pi over 6 is a nice fraction, whereas the other ones are like root 3 over 2 or stuff. So sine of 7 pi over 6 is negative 1/2. So you get 1 minus negative 1/2, which is going to be 3/2. And 3 pi over 2, sine of 3 pi over 2 is negative 1. So 1 minus negative 1 is going to be 2. And at 11 pi over 6, same as 7 pi over 6, sine of that is going to be negative 1/2. So 1 minus negative 1/2 is 3/2. And finally, we're all the way back around to 2 pi, which is going to get us back where we started. So here's how this is looking. So with theta is 0, which means we're pointing to the right, our radius is 1. And then pi over 6, which is maybe like this angle here, our length is 1/2. Right about there. And then at pi over 2, our length is 0. With our length 0, we're always at the origin. And then 5 pi over 6, which is this way, our length is also that same 1/2. And then at pi, which is this way, our length is 1. And then 7 pi over 6, which is this way, right? It's just the opposite of pi over 6. Our length is 1/2 or 3/2. So like at 3 pi over 2, which is straight down, our length is 2. And at 11 pi over 6, our length is also this way here. So it kind of looks like this. It's kind of pointy right here. It's called a cardioid. Kind of looks like a heart. So, what's the slope of this graph at the point 1, 0? What's the slope? It's always weird for points. So I will point out, just in case you hadn't noticed, for points that are on the x-axis, their polar and their rectangular coordinates are the same. At the point 1, 0 in rectangular is over 1 up 0. The point 1, 0 in polar is angle of 0, which is straight to the right, and a radius of 1, which is 1 to the right. So that can always be, that can be a little confusing sometimes. So I want to find the slope right there. So I'm interested in finding for r equal to 1 minus sine theta, I really want to know what dy dx is. Well, we've done this before. We know how to find dy dx for parametric equations. So dy dx for parametric is dy dt over dx dt. So dy dx for polar is dy d theta over dx d theta. But the problem is we have to figure out what x and y are in terms of theta. So here's what we know. So we're going to go back to our polar coordinates equations. We know that x is equal to r cosine theta, y is equal to r sine theta. But we know that r is 1 minus sine theta. So typically what people do is they say, okay, this is like our f of theta. So what we're going to do is we're going to say that x is really equal to f of theta times cosine theta. And y is equal to your function of theta times sine theta. It's going to get a little bit messy. So dy dx is going to be dy d theta, dx d theta. That's going to be, well, the derivative of y is going to be, we have to use the product rule. It's going to be f prime of theta times sine theta plus f of theta times the derivative of sine, which is cosine. And dx d theta is going to be f prime of theta times cosine theta. And then the f of theta times the derivative of cosine is negative sine theta. So that's how we're going to find dy dx. So in this particular case, our f of theta is 1 minus sine theta. So our dy dx is going to equal, so the derivative of 1 minus sine is going to be negative cosine theta. So negative cosine theta times sine theta plus f of theta is 1 minus sine theta times cosine theta, all divided by same thing on the bottom. So f prime of theta again is negative cosine theta times cosine theta plus, sorry, minus 1 minus sine theta times the derivative of, sorry, oh, that's right, and 1 minus sine theta times sine theta, apologies. It's a bit of a formula. So then we probably should simplify this, or not. We can just plug, let's just plug in 0. So plugging in dy dx, plugging in theta equals 0, we're going to get, let's see, so cosine of 0 is 1, sine of 0 is 0. So we're going to get 0 plus 1 minus, so we get 0 plus 1 minus 0 times 1 over negative 1 times 1 minus 1 minus 0 times 0. So end up getting 1 times 1 over negative 1 plus 0, just negative 1. So at this point, the slope of the line is negative 1, which seems reasonable, right? That looks like it could be negative 1 for sure. Questions about that? So again, I just want to point out, if R is some function of theta, this is how you find dy dx. It's not pretty. Basically, I mean, quite literally, we're just taking the parametric equation and plugging in, right, using this as what x is and this as what y is. Okay. I don't want to erase the other side just yet. Yeah, I still like this picture. So I want to do two things. I want to find the length and the area of the cardioid. Let's find the length. Well, it's still the same idea, right? The length of a curve is the integral of ds, right? So the length is the integral of ds, which is the integral of the square root of, it's either 1 plus dy dx squared or 1 plus dx dy squared, or dx d theta squared plus dy d theta squared, right? And we're going to do it that way. So it's going to be dx d theta squared plus dy d theta squared dt, where theta goes from 0 to 2 pi. Sorry, not dt, deep theta. All right, well, that's going to be gross, right? Oh, sorry, I erased my derivatives. Apologies. So remember, so x is equal to f of theta cosine theta, which is 1 minus sine theta times cosine theta. And y is equal to f of theta sine theta, which is 1 minus sine theta times sine theta. This is going to be really kind of gnarly, right? We have to take this so we're going to get something pretty gross. So it's going to be the derivative of this, which requires the product rule. Yeah, no, really, it is. Yeah. So it's going to be negative cosine theta times cosine theta, so negative cosine squared theta, plus 1 minus sine theta times the derivative cosine theta. And that's the derivative of this. We double check and make sure that's right. It's the derivative of this, which is negative cosine times cosine, and then the derivative of this, which is this times the derivative of this, which is, yeah, that looks good. So we're going to take that and we're going to square it, plus then the derivative of this squared. So it's going to be, again, negative cosine theta times the sine theta, plus 1 minus sine theta times cosine theta. Line squared. That looks pretty gnarly. Yeah, I don't really want to do all that. So yeah, it's really kind of a giant pain in the butt. Let's take a look here. Oh, that's interesting. So actually, so before we do this, oh wow, it really actually simplifies. So it's probably, let's back it up. Sorry. Oh, let's be a little more careful. So I actually don't want to write all of this. What I really want to do is actually just write so it's the derivative of this. Let's write it in the not specific way. So it's going to be the derivative of this, which is going to be f prime of theta times cosine theta quantity, or sorry, plus f of theta times the derivative of cosine theta, which is negative sine theta. Squared, and then the derivative of this square, which is going to be f prime of theta times sine theta plus f of theta times the derivative of sine, which is cosine theta squared. Now, I don't really want to show all the work because it's kind of gross, but I could if you guys want me to. So let me tell you the result, and then if you really want me to, I'll show you how we get there. So the result, I guess I should not write these angles in just yet. The result is that this ends up equaling the integral of the square root of f of theta quantity squared plus f prime of theta squared. Or the integral of the square root of r squared plus d theta squared. Which is much easier than trying to jam all this stuff in here. So would anybody like me to talk about how to get from here to here? I'm happy to do so. I'm mostly happy to do so if you would like. But really it's just multiplying it all out, combining terms, seeing some true identities, and then canceling stuff. All right, it doesn't sound like anybody wants me to do that, which is great because I really didn't want to do it. But that means then that instead of trying to take this and throw it in here, we can just say that our arc length, the length of our thing, is going to be the integral from 0 to 2 pi of the square root of r squared, and r was 1 minus sine theta, 1 minus sine theta squared, plus the derivative of that squared. The derivative of that's going to be negative cosine theta squared. That's a lot easier to work with than what I was about to do. So let's take a look. Integral from 0 to 2 pi. For multiplying this out, we get the square root of 1 minus 2 sine theta plus sine squared theta plus cosine squared theta. That's equal to 1. So here's what I've got. I've got the integral from 0 to 2 pi of the square root of 1 plus 1, so 2 minus 2 sine theta. And then you might ask yourself, what the heck do I do with that? This is one of the trickier integrals to deal with. It does require a few steps. I'm going to factor out the 2. I'm left with a 1 minus sine theta. I'm going to take that 1 minus sine theta over 1. I'm going to multiply it by 1 plus sine theta over 1 plus sine theta. And then we'll have the integral from 0 to 2 pi of the square root of 2 times 1 minus sine theta times 1 plus sine theta is cosine squared theta over 1 plus the sine theta. Interesting. So I'm about to encounter an issue which I'm going to try and fix. And the issue is the square root of cosine squared theta is actually the absolute value of cosine. When cosine is negative, that's a problem. So what I'm going to do is I'm going to say, well, I'm going to do the integral. The square root of 2 is the square root of 2 Cosine squared theta is cosine theta divided by the square root of 1 plus sine theta. What I'm going to do is instead of going from 0 to 2 pi, I'm going to cut it in half and go and do double it. But the problem is I have to cut it in half the right way. I can't cut it in half, right? Because this is 0 to pi wouldn't be cutting it in half. What I really need is negative pi over 2 to 0 to pi over 2. So I'm going to cut it in half that way. And then we can do a u sub. Sorry, way over here. We can let u equal 1 plus sine theta, and the du will be cosine theta d theta. So then our integral is going to become 2 root 2 times the integral of du over the square root of u, or u to the minus 1/2 du. Our limits of integration are going to change, right? Let me double check. I'm doing something funky here. Yeah, we should change them. So, right, if theta equals 0, sine of 0 is 0, so u is going to be 1 plus 0, which is 1. Oh, I'm starting at the wrong limit of integration. Right, I'm no longer going from 0 to 2 pi, I was going from negative pi over 2 to pi over 2. Sine of negative pi over 2 is negative 1, which is going to be 1 minus 1, so that's going to be 0. And for pi over 2, sine of pi over 2 is 1, and 1 plus 1 is 2. So that's what we get. Okay, we're almost done. It's a long problem. So we're going to get 2 root 2. The integral of u to the 1/2 is, sorry, u to the negative 1/2 is u to the positive 1/2 divided by 1/2, or 2 times the square root of u from 0 to 2. So we end up with 2 root 2 times 2 root 2, which is 2 times 2 times 2, which is 8. All that for 8. It's kind of neat, though. Right? It's kind of neat that this funky looking curve is exactly 8 units long. Whatever units are.
Wait, James.
Yeah.
The 8 units, is that just the perimeter?
Yep, that's the perimeter.
Oh, okay. Just want to make sure. Thank you.
Yeah, of course. Hopefully no one ever asks you an arc length question, because as you can see, I mean, they're not always so terrible, but the starting formula is pretty funky and it just kind of gets worse. So yeah, arc length is not super nice. Let's talk about the area of the cardioid. So the idea for the area using polar coordinates comes from kind of like the idea of the area of a sector of a circle. So you have a sector, if you have a circle, this angle, let's say this angle is theta, the area of that sector, and then with the radius of r, is 1/2 r squared theta. That's the idea. So what we're going to do for our cardioid here is we're going to, instead of having like a small change in x, we're going to have a small change in theta. So let's say like, right, from here to here. And we want to estimate the area of this sector looking thing. Now, I will point out, it's obviously not a true sector. Right? A sector of a circle is a slice of pi, where the distance from the, whatever, the vertex here or the center is always the same. Right? Whereas here, right, along this curve, the distance from here to the origin isn't always the same. But just like how when we did rectangles under a curve, right, they weren't actually rectangles, they were just approximating rectangles. Same idea here. So the area of that sector, is 1/2 times the radius, whatever that is, times the angle, which is a d theta, right? It's a small change in theta. And then we're gonna add up all the areas of the sectors. So the total area is going to be the integral of 1/2 times my r, and where r is a function of theta, d theta. So that's how you find the area of enclosed by some polar curve. Is you do the integral of 1/2 times the function r as a function of theta squared d theta. Which is seemingly less terrible than what we were just talking about. So the eraser is really gross. Yeah, super funky looking. Okay, so in this case, our area is going to be the integral from, let's do 0 to 2 pi. Let's see what that gets us. 1/2 times 1 minus sine theta quantity squared d theta. Well, it certainly looks less tricky than the other one we were doing, right? There isn't like a square root, first of all, so that's an improvement already. Screenshot here, everyone can see here. So let's see. We get to multiply out this. That's going to be 1/2 times the integral from 0 to 2 pi of 1 minus 2 sine theta plus sine squared theta. Okay. And then I will, you could also half and double like we did before, but there isn't the same concern. So you could do this as like 2 times 1/2 times the integral from negative pi over 2 to pi over 2 if you wanted to. But anyway, so we need to replace sine squared, right? Sine squared is 1 minus cosine of 2 theta divided by 2, or 1/2 of 1 minus cosine of 2 theta. All right, so then I guess we can integrate this. So we're going to get 1/2 times integral of 1 is theta. Integral of 2 sine theta is going to be negative 2 cosine theta is going to be a positive 2 cosine theta, right? So derivative of 2 cosine theta is negative 2 cosine theta, negative 2 sine theta. And then the integral of 1/2 times 1 is just going to be 1/2 times theta. The integral of 1/2 times negative cosine theta 2 theta is going to be minus sine of 2 theta divided by 4. Because if you take the derivative of that, you get cosine of 2 theta times 2, and the 2 over 4 reduces to 1/2. Okay, 0 to 1, what kind of crazy thing am I writing? That's a 2 pi, not a 1. So let's see what happens. You plug in 2 pi, you get 2 pi. Cosine of 2 pi is 1, so you get 2 times 1. 2 pi divided by 2 is pi. Sine of 4 pi is 0. Minus, plug in 0 and you get 0, cosine of 0 is 1. 0, sine of 0 is 0. The 2 and the minus 2 cancel out, so you get 1/2 of 3 pi, so you get 3 pi over 2. Interesting. Okay, I'm going to go get some more water. I ran out of water. I'll be right back. Just really 1 second. All right. So let's do some examples. Well, one example, one kind of gnarly example. So we'll do this example, and then there's another example someone asked me about. And then there's one other parametric question someone else asked me about. And that's all I've really got on schedule. If you guys have other questions, you're certainly welcome to ask them. So let's see here. So I want to find the area of the region common to. So I want to find the area of overlap, essentially, of the two curves are equal to 1 minus sine theta, the cardioid we just looked at, and r equal to sine theta, the circle with a diameter of 1 centered on the y-axis. So it's going to look like the following. I should have erased my cardioid. So my cardioid has these points here. Sorry, I'm trying to draw something that looks pretty good. Sure that's like over here. Okay, it's not perfect, but it's fine. And then the circle r equals sine theta has a center at 1/2, 0, 1/2, and does this kind of deal. So I'm looking for this area here and this area here. And I would, first of all, I would use symmetry to say, I'm going to find that area there and double it. So let's actually kind of get a closer look. So let's say, I'm going to blow that right side up. So I've got my, here's my r equals sine theta, and here's my r equals 1 minus sine theta. And I want to find the area of that. So first of all, I need to find where these intersect each other. So let's see, saying 1 minus sine, let me erase this. I think I can be done with this. Sure. So I'm going to set 1 minus sine theta equal to sine theta. Add sine theta, so 1 is 2 sine theta equals 1/2. So theta is going to be pi over 6. So this angle here that's pi over 6. So then I want to find the area of each of these parts. So basically, the idea here is that from an angle, so my angle is 0, I'm right here, and my angle is small, like less than pi over 6, my radius is like that. So to get this green part of the area, right, the green part, the area is going to be the integral from 0 to pi over 6 of 1/2 times the radius, which is sine theta squared. The red part, on the other hand, is all this. From an angle of pi over 6, getting larger and larger and larger until the angle gets closer and closer to pi over 2, right? Because when the angle is pi over 2, sine of pi over 2 is 1, and 1 minus 1 will be 0, so the radius will be 0. So the red area is going to be the integral from 0, sorry, not from 0, from pi over 6 to pi over 2 of, again, 1/2 times your function squared. And then we're going to double that. So let's see what we've got here. So our total area enclosed by these two curves is going to be 2 times I can factor out the 1/2 from each of these. So 1/2 times the integral from 0 to pi over 6 sine squared theta plus 1/2 the integral from pi over 6 to pi over 2 the integral of 1 minus sine theta quantity squared. Oof. All right, it's gonna be a little bit of work, but we can do it. Notably, we can factor out the 1/2 and the 1/2, and 2 times 1/2 would be 1. So I'm gonna rewrite this as just basically this integral without the coefficient plus this integral without the coefficient. That's nice. Yeah. Let's do that. So we're doing the integral of from 0 to pi over 6 of sine squared theta plus the integral from pi over 6 to pi over 2 of 1 minus sine theta squared. And let's rewrite 1 minus sine theta squared as 1 minus 2 sine theta plus sine squared theta. I might do something to make my life a little easier here. Here's what I notice. I've got a sine squared theta here and sine squared theta here. So what I could really do if I wanted to is I could rewrite this as the integral from 0 to pi over 6 plus pi over 6 to pi over 2 of sine squared theta plus the integral from pi over 6 to pi over 2 of 1 minus 2 sine theta. Do I need to explain that more? I'm happy to if you guys would like me to. All I said was the integral from 0 to pi over 6 of sine squared plus the integral from pi over 6 to pi over 2 of sine squared is equal to the integral from 0 to pi over 2 of sine squared. And then I still have the rest of this over here. So then we have to use our not favorite trig identity. This is going to be the integral from 0 to pi over 2 of 1/2 1 minus cosine of 2 theta. Let's go and start integrating this. This is going to be the integral of this is going to be theta plus 2 cosine theta from pi over 6 to pi over 2. Integrate this. So we're going to get theta minus sine 2 theta all over 2 from 0 to pi over 2. Plus, plugging in pi over here, you're going to get pi over 2 plus 2 times cosine of pi over 2 cosine pi over 0 minus pi over 6 plus 2 times cosine of pi over 6. Cosine pi over 6 is root 3 over 2. It's going to be 2 times root 3 over 2. I guess that's just root 3. Okay. Then we're going to simplify this. This is going to be 1/2 times pi over 2. Sine of 2 times pi over 2. Sine of pi over 2 is 0. So minus 0. Minus, plugging in 0, you get 0 minus 0. Plus pi over 2 minus pi over 6 minus the square root of 3. So it looks like our final answer is a pi over 4 plus a pi over 2 minus a pi over 6 minus the square root of 3. You should combine that, right? That's really 3 pi over 4 plus 6 pi, sorry, that's 3 pi over 12 plus 6 pi over 12 minus 2 pi over 12 minus root of 3. So we end up getting 9 minus 7 pi over 12 minus root 3. Well, that's funky. Questions about that? Right. Let's go ahead and look at this problem that someone asked me about, which seemed challenging. No, it is not just seem challenging, it is challenging. But still going to employ the same idea. Basically, that when you're finding the area, the idea is you're integrating 1/2 r squared d theta, and r is just how far out you are from the origin. Although this one did take me a minute to kind of figure out how to set it. Here's the setup. We have two circles that overlap, one of radius 7, one of radius 9. So the radius 7 one is centered at the origin. Kind of looks like this. And so r equals 7. That's the point 7, 0. The radius 9 one is centered at 9. So like it's okay. I don't really care about that. I don't care about that part of it. Not my best circle. And we want to find this area. Okay. So first of all, so what I really want to do, I really want to first just deal with the top half. And basically the idea is I want to find, how do I say it the right way? Yeah, I need to draw a better picture. Let me just draw you the top half so I can see what I really mean. It was hard for me to get this picture to look exactly right on my own here. Yeah, okay, I want that. So I've got this top half of this. I've got my other circle doing, circly things like that. And the thing is, we actually, so like, I'm gonna draw this other line here. So the line that goes straight from here to there. Yeah. So here's the idea. I want to find essentially this area of this big semicircle. Well, actually, sorry, what I really want to do is find the area from the black. So not the area of the entire semicircle, right? Everything to the right of this minus this part here. Okay, so basically, you need to find this angle. So to find that angle, well, that angle happens to be where both circles intersect each other. The smaller circle being the circle just of radius 7, literally the equation for the smaller circle is r equals 7. That's it. It's not very exciting. The bigger circle with a radius of 9, centered at 9, is r equals 18 cosine theta. So we set those two equal to each other, we can figure out what theta is. So 7 equals 18 cosine theta, divided both sides by 18. Take the inverse cosine of both sides. So inverse cosine of 7 over 18 is equal to theta. So this angle here is the inverse cosine of 7 over 18. My favorite number. All right, so now the idea is from theta equals 0 to theta equals inverse cosine of 7 over 18, we want the area of this bigger shape minus the area of the smaller shape. Well, great, we can totally do that. We know how to find the area of things. So basically, we're going to find the area is going to be the area of the big thing. That's going to be the integral from 0 to inverse cosine of 7 over 18 of 1/2 of your function, which is 18 cosine theta, quantity squared d theta. Minus the integral from 0 to inverse cosine of 7/18 of 1/2 7 squared d theta. And really, we totally could have written this as one integral. And what I really extra want to point out here is this is just like finding the area between curves, right? Usually we find the area between curves is the top curve, right? You do the integral of the top minus the bottom. Well, now here it's the integral of the further away function from the origin that minus the closer function. Essentially, we're trying to write, right? So to find the area of this smaller one, we're doing, here are our radii up until we get to the, the last one there. And then we're subtracting that away from this larger one. I was getting all bent out of shape because I was kind of thinking about this little sliver over here. That sliver over here isn't part of the game at all. And that little sliver over there is beyond what we want. Which is good. And we only want the stuff that's specifically right. All this here. You don't have to worry about that over there. I was trying to do the problem differently at first, and I was kind of getting jammed up. So erase that picture. Yeah, I guess I don't have to erase that picture. So we're gonna do this integral. Let's write it as one integral. So we're gonna do the integral. 1/2 the integral from 0 to the inverse cosine of 7/18 of 18 cosine squared. 18 cosine theta quantity squared. 18 squared is 324. So it's going to be 324 cosine squared theta minus 7 squared, which is 49. All right, and the rest is just doing terrible integration that we've done before. So we're going to get 1/2 cosine squared theta is going to be, picked some really nice numbers for this. I'm kidding. Cosine squared theta is 1 plus cosine theta 2 cosine 1 plus cosine 2 theta all divided by 2. 324 divided by 2 is 162. That's going to be 162 times 1 plus cosine of 2 theta minus 49. Okay, so we've got the integral from, 1/2 the integral from 0 to inverse cosine of 7/18 of 162 times 1 minus 49 is 113. So 113 plus 162 cosine theta. Cosine 2 theta. Okay, now we integrate. Integral of 113 is 113 theta. Integral of 162 cosine 2 theta is 162 sine 2 theta over 2. So I'm going to write that as 81 sine of 2 theta from 0 to inverse cosine of 7/18. Now here's the deal. Like before, when we were doing trig substitution, I really don't want to write my answer as sine of 2 times inverse cosine of 7/18. I want to use a trig and need to make it nicer. So I'm going to write this as, let's distribute, let's leave the 1/2 out. 1/2 113 theta plus sine 2 theta is 2 sine theta cosine theta. This is going to be 81 times 2, so 162 sine theta cosine theta from 0 to inverse cosine 7/18. Okay, so then I'm going to draw a triangle. If inverse cosine of 7/18 is equal to theta, then cosine of theta should equal 7/18. And this third side should be the square root of 18 squared minus 7 squared. 324 minus 49, which I'm betting is probably not a square number. Let's see. 324 minus 49 is 275, which is not a square number. Oh well. It does have a square. I mean, it does have, it's what? It's 11 times 25, I think. Yeah. So you could say it's 5 square root of 11 if you really wanted to. Anyway, here's what we get. We get 1/2 times 113 inverse cosine of 7 over 18. Beautiful. Plus 162 times sine of theta, which is 5 root 11 over 18, times cosine of theta, which is 7 over 18. Minus plug in 0 and you get 0, right? 0 here gives you 0, 0 here gives you 0. And then, this is only half of what I wanted to double it. Gross. Yeah, real gross. So my final simplified answer would be 113 inverse cosine of 7/18 plus 162 is really just half of 30 of 18 squared. 162 is 81 times 2, so it's 2 times 9 times 9. So I can cancel a 9 and a 2 there, and a 9 with a 9 there. So I'm really left with 35 root 11 over 2. What a weird answer. But not, I mean, terrible, just atypical. Polar coordinates, real, they are useful. They're definitely useful when you get to 21D. And you'll start integrating things. You'll start doing three-dimensional graphing kind of stuff. I mean, less graphing. You'll look at three-dimensional things, and sometimes you'll do it in rectangular coordinates, and then you do it in polar, which are called cylindrical coordinates when you add a third dimension. So they are useful. All right, let's look at this. Not last, but this next question. This last student, this last question that a student asked me.
Jim?
Yeah.
A good question on what's on the back of the board.
Sure.
So from the 162 parentheses 1 plus cosine of 2 theta minus 49 d theta, how did you go from that before that to that?
From here to there?
Yeah.
Sure. So I replaced cosine squared theta with 1 plus cosine of 2 theta divided by 2. And then I did 324 divided by 2 is 162.
Oh, okay. That makes sense. Thank you, James.
Oh, yeah. Okay, so switch gears here. Back to parametric. Find the area of the surface obtained by rotating the curve x equals 2t minus 2/3 t cubed, and y equals 2t squared around the, from t equals 0 to 1, around the x-axis. So we know that for surface area, the very general formula for surface area of a curve rotated around an axis is the integral of 2 pi times your radius times ds, where ds again is the square root of things, derivatives squared, right? It's the square root of either 1 plus dy dx squared, or 1 plus dx dy squared, or dy dt squared plus dx dt squared, or dy d theta squared plus dx d theta squared, right? Lots of options. So in this case, everybody should know the answer to this. If we're going around the x-axis, what's our radius? Is it x or is it y?
Should it be y?
Yeah. You can type in the chat. The chat's right there. I know you can. I never. Okay. Yeah, and the radius is y. So the radius in this case is 2t squared. So this is going to be the integral from 0 to 1 of 2 pi times the radius, which is 2t squared. And then the ds is going to be the square root of the derivative of this squared. So derivative of that's going to be 2 minus 2t squared, right? Because the derivative of 2/3 t cubed is 2/3 times 3t squared. And then the derivative of y is going to be 4t quantity squared. It looks like things are probably going to work out nicely. Let's do it. So let's see. So I'm going to factor out the 4 pi. So 4 pi integral from 0 to 1 t squared times the square root of. So this is going to multiply out as 4 minus 2t squared times 2 minus 4 minus 8t squared plus 4t to the fourth. And then my bet is I'm going to be adding a 16t squared to flip this middle thing from negative to positive. And I am, right? 4t quantity squared is 16t squared. So then I'm going to have the integral from 0 to 1, 4 pi times that, of t squared times the square root of 4 plus 8t squared plus 4t to the fourth. And then we can factor that essentially like that, but with a plus sign in the middle. So that's going to be 4 pi times the integral from 0 to 1 of t squared times the square root of 2 plus 2t quantity squared. Sorry, 2t squared quantity squared. But the square root of 2 plus 2t squared is just 2 plus 2t squared. So I'm going to get 4 pi integral from 0 to 1 of t squared times 2 plus 2t squared. Then we can distribute the t squared. We get 4 pi integral from 0 to 1 of 2t squared plus 2t to the fourth. And finally, we can integrate. We get 4 pi times 2t cubed over 3 plus 2t to the fifth over 5. From 0 to 1, plugging in 1, we get 4 pi times 2/3 plus 2/5. And plugging in 0, you get 0. So let's see. 2/3 plus 2/5 is 10/15 plus 6/15. So we're going to get 4 pi times 5, yeah. 10 plus 6 is 16/15. So we're going to end up with 64 pi over 15. Good times.